of this video is to go over RC circuits. So let's start off by going over our learning goals and objectives. The first one is to understand that capacitors introduce time dependence to the current in a circuit. The second is to know how to and be able to draw circuits initially and at long or infinite times. And the third is to know what the time constant for an RC circuit is and how it relates to the charge stored in a capacitor. Okay, so let's start off by just first discussing a uncharged capacitor. So the uncharged capacitor will look something like this. We'll have the capacitance C. The charge Q will be equal to 0 because it's uncharged. And then there's also a voltage Vc from the capacitor. So if we say that this is the charge at time equal to 0, so now our charge is going to be a function of time. So our charge at time equal to 0 is 0. Then I'm going to let you pause the video for a second and think what the voltage across the capacitor will be at this time. So what's V of C at t equal to 0? Alright, did you at least think of something in your head? There is no harm in saying anything. I'll never know. No one will ever know. This is the beauty of it. So the voltage across the capacitor is the charge on it, Q, over C, and this is going to be at t equal to 0. So now, this, as we said, was 0 over C, so 0. So the charge, or the voltage across a capacitor when it's uncharged, is 0. So one way to write this is to say that initially, capacitor is just a wire, or in circuit terms, it's a short. So there's no potential difference across this. So the V sub C is equal to 0. No potential difference, it's a wire or a short. Okay. So still looking at the uncharged capacitor, let's look at or the case where the capacitor is initially uncharged. So as t goes to infinity, the capacitor is being charged up by some voltage source, so it's connected to some voltage source, and we want to look at the capacitor. So we still have this capacitor, capacitance C. It's going to have some time-dependent charge. It's also going to have some time-dependent voltage. So now, after the capacitor is charged up for some infinite amount of time or some really long time, the charge on it is just going to be fixed. So it's going to be some Q infinity. Now, if there is some Q infinity, think for a second and trying to decide what your voltage will be. You have an answer? Great. So as t goes to infinity, so this should have been t goes to infinity up here. This is going to be the Q t going to infinity over the capacitance C, and that's going to be equal to Q infinity all over the capacitance C. So the big idea here is this is a constant. So that's great. So what this says is at infinite times, a charging capacitor will approach a constant potential difference. So the way that we write this is we draw this. This is called an open. And then this has some constant potential difference, V infinity, across it. So the big idea here is there's no current flowing in the circuit, in this part of the circuit anymore. it is at whatever potential it's at, and now charge is just stationary. So there's the plus Q up there. So now let's do an RC example now that we know this. So uncharged capacitor. So we're going to have circuit looks like this. Resistor R, capacitor C, and then the negative terminal, so this is a voltage V. This right here is just a switch. So the idea is right now the circuit is broken, so no current will be flowing anywhere. And once we close this switch, then we'll be able to have some current flowing. And more or less it's so that everybody can be on the same page as to what's going on. So let's now shut this switch. So we close the switch, and then a current I of T comes out. So this voltage source is always at a constant V, but this current will be a function of time because it's going to come over here and charge up the capacitor. So now what we need to do is we need to redraw this circuit such that it reflects what happens initially. So we're going to have some voltage source, a resistor, and then right here is going to be a question mark that you're going to think about what it's going to end up looking like. So this is going to be potential difference V, R, then I of T equal to 0. So this is for T equal to 0, right when the switch is flipped. So think about what this will look like, especially in reference to what we just went over. Okay. Have an idea? Great. So all this is going to be is a short. So there is no potential difference across this capacitor initially because it's uncharged. So this is what we start off with. We can go and do Kirchhoff's loop law to figure out the voltage which drops around this loop. So we'll get minus V plus V sub R plus V sub C equal to 0. But we already went over that the V sub C is 0, so we can get rid of that. So we get V equals V sub R, or by Ohm's law, I of T equal to 0 times the resistance is that, or I of T equal to 0 equals V over R. So we come over here and make a little sketch. T, and then, sorry about that, I of T right here. What we see is we're going to start at V over R. That's T equal to 0. So we'll take this to be 0, 0. Okay, so that's one thing. Now let's go back over here and we will try and figure out what this circuit looks like for T approaching infinity. So take a second, figure out what's going to be right in there. Got an idea? So this will just be an open, because the capacitor is fully charged up, and we can go around and we can do the loop. So it's still minus V plus V sub R plus V sub C equal to 0. So as t goes to infinity, this charge, the capacitor is fully charged, so there's no longer any current flowing through the circuit, because you can think that as positive charge comes down here, once it's full on the capacitor, it no longer lets the current flow throughout this part of the circuit anymore. So now there's no current. If there's no current, there's no voltage drop across the resistor, so this is just equal to 0. We see that the voltage across the capacitor is equal to the voltage across the potential source. So at long times, the voltage across the potential source is equal to the voltage across, I think I just repeated myself. Oh well. So now we can draw this little point right here. We can say, okay, that's infinite like. So it's, pretty close to 0. I just drew it a little bit off the axis so you could see it. Yeah, well. Okay. So now what we need to do is we need to sort of figure out what this function looks like in between here. So more or less, what ends up happening is the charge that comes through here and builds up onto the capacitor is a continuous function. So what that means is charge doesn't come in arbitrarily huge amounts, so you can't just have this infinite jump in potential. It has to be smooth. So this function has to smoothly go, and the current decreases from start to finish. So it's going to be smooth, nice and pretty, and it's just going to come down and kind of look like that. It shouldn't go up like that. That was just my poor handwriting. So it's just going to smoothly flow out here and get less and less and less. So now what we're going to do in this next part is we're going to figure out what actually is the mathematical form of this function. So it'll end up being exponential, but it's hard to say, oh, is this an exponential? Is this a polynomial? So is this, really just, x squared or e to the minus x? Well, from this, qualitatively, you can't quite say, but that's just life. So we're going to do the math and the physics to figure out what this actually looks like. So this is the current, and we could also sketch the charge on the capacitor as a function of time. So this will be time, this will be charge. So it starts off uncharged, and then there's some infinite value over here. So V sub C equals V, or Q over C equals V, Q equals CV. So this is, so this height up here is CV, and then this is Q of T. So it's going to start off at 0, and it's going to end, it's going to infinitely approach this. It's going to be a smooth, continuous function, so we just kind of go like that. And then the voltage is going to look exactly the same, because you just are going to divide this by, you're just going to divide this by C, and it would just look exactly the same, but with V. Okay. So let's redraw that RC circuit. Now what we're going to do, so we know what this looks like at t equals 0, t equals infinity, and now what we want to do is figure out how it goes from one to the other. So we'll write down Kirchhoff's loop law. So we'll do, that's going to be offensive to the eyes, so I'm going to go with black. So we're writing down the loop, so it's minus V plus V sub R plus V sub C equal to 0. This is an intermediate time, so we'll have some I of t, and this is going to be some intermediate time, so neither the voltage across the resistor nor the voltage across the capacitor will be 0. So what we have to do is we need to substitute in what these are. So minus V plus I sub t times R plus Q of t over C equal to 0. So now what we need to do is we need to make this all be one function so that we can solve for it. And the trick that you need to remember is how the current and the charge are related. And it's pretty simple. So current is just the time derivative of the charge. So more or less, as most of you are familiar, current is just how much charge is moving per time. So now what we do is we substitute this in to right here. So we have minus V plus dq of t over dt. That has to be multiplied by r just because I was multiplied by r, plus q of t over c equals to 0. Now what we have is we have some constant potential V, we have a time derivative of Q, we have Q, and we have 0. So this is a differential equation, and we can either solve for it, but usually in this class we just guess the answer. So the answer that will work will be Q of t equal to CV1 minus e to the minus t over RC. So what we can do is we'll remember this, and then we'll take this derivative, we'll do the physics 171 thing, we'll guess a solution, and then we'll put it in. This is a perfectly valid way to solve differential equations. We could have solved for this explicitly, but I think people would have just been upset. So CV stays around because it's just a constant. The derivative of 1 is 0. The derivative of e to the x is itself back. And then we need to take the derivative of this because it's a function of t. So chain rule, chain. 1 over RC. The negative signs are going to cancel out, and then the C's are going to cancel. So the negatives cancel, C's cancel, and we get V over R. So voltage divided by resistance, that'll give you a current. And then you're going to get e to the minus t over RC. So this is great because we wanted to know the functional form of the current, and we can just put this back into here. So we're going to get minus V plus V over R e to the minus t over RC plus CV1 minus e to the minus t over RC all over C equal to 0, so the C's will cancel. This was multiplied by R, I forgot that, so just this part right here. The R's will cancel, we'll get minus V plus V e to the minus t over RC plus V, so we multiply in V, we get V times 1, that's V, and then a minus V e to the minus t over RC equal to 0. Plus and minus V's cancel, V e to the minus t over RC's cancel, and we get 0 equal to 0, and voila, it's a solution. Time for great celebration and merriment. All right, so let's highlight a couple big things. The current goes as e to the minus t over RC, and the charge goes also e to the minus t over RC, so this exponential governs the time dependence. This one, at t equals to 0, it's going to be 1 minus e to the 0, which is 1, so it starts off as 0. This one, e to the 0 is 1, so it starts off at a big value and goes down, whereas this starts off at 0 and then goes up to its infinite value. So these are two key results to remember. So we can clear that out. We can go back to what the current as a function of time looks like. So t I of t, and it starts off at v over r, and then it just decays exponentially. So, more or less, what this says is this is the current as a function of time, and if we integrate the current, which I know you hate integrals, but an integral is just the area under the curve. So the amount of area under the curve here tells you the charge, because it's I of t times dt. So the area underneath the curve says how much charge there is. So at t equals to 0, it's just, infinitely thin, so there's no charge. And then as you go out towards infinity, you add up all of the current times the dt's, and you end up with the amount of charge that's stored on the capacitor. So what you see, and the reason why this goes down, is because as you put more charge onto the capacitor, it's harder to put even more charge on there. So like charges repel, so as you are fitting more and more charges into there, so as you take smaller and smaller steps, or same size steps in dt, you get less and less charge that you add on, but it all adds up to whatever total charge you have, and that configures into the voltage. So getting the last little, tiny bit of a percent of the total charge that you can store on the capacitor takes a really long time, because it's really hard to force it in there. So the last thing that I want to go over is just the time constant. So this is going to be e to the minus t over RC. RC is known as the time constant for this circuit, which is usually written as tau. This is the amount of time it takes for the value to drop from its initial to 1 over e. So this horizontal distance is tau. So more or less, so tau, time to drop by 37%, 1 over e. So more or less the way you can think about this, in 5 taus, the current will have ended up being 0.7% of what it initially was, or if you think about the voltage or the charge, it ends up being 99.3% of its long time infinite value. So this is, more or less the time that it takes to be fully charged, because 99.3 is pretty much 100%. So the last thing that I will leave you with is 2 questions. So if we want to charge faster, how can we do that? And if we want to charge slower, how can we do that? So this is both asking, just in a pictorial sense. So this tau is going to govern the this tau is going to govern the time constant of the circuit. So just looking at the basic equation, how can you make this longer or shorter? And then also from an electrical circuit standpoint, how would you make this multiplication between the resistance and the capacitance smaller? So how smaller or larger? So more or less, how could you make the resistance larger? How could you make the capacitance larger? How could you make a resistance smaller? How could you make a capacitance smaller? If you want to post your thoughts in the comments section, and feel free to make a discussion. Thank you.